Hey everyone, and welcome back to the channel. This is the second video in our Agent Factory series on optimizing agentic applications. In the previous video, we explored semantic caching and how it can significantly reduce costs while speeding up your applications. Today, we are solving another real problem. What happens when your agent needs access to many tools? In that scenario, you will notice performance drops, the agent misses tools, and accuracy goes down. You'll have two options at that point. Option 1, break your system into specialized sub-agents, each with fewer tools. Option 2, give your agent a smart way to find the most relevant tools for each task. Today we are focusing on option 2. I have built a test system with 70 e-commerce tools, and we will compare 4 different strategies to see which one wins on cost, speed, and accuracy. Let's dive in. This is the notebook that I want to use for this project. For the LLM agent, I want to use GPT-4o Mini. As you can imagine, this is a very powerful LLM by itself. So the importance of these strategies will become very clear, especially when you are working with open source models. But even with GPT-4o Mini, we are going to see the difference together. These are the different strategies that I've already implemented, and we are going to see the result together. The first one is called naive, and we pass all the 70 tools to our large language model. The second strategy is called category-based, which we route to category first, then use 15 tools together. You will understand the meaning of category in a moment. We have a retrieval-based strategy in which we use a Chroma database to find top-K relevant tools. And finally, we have a hybrid strategy. And for the metrics, we are going to see the accuracy, latency, token usage, and cost estimation. These are the tools that I prepared for this simulation. So we have functions, we have a description, and we also have a mock output. And as you can see, I didn't implement any code into any of these functions or tools in our simulation. So when I'm talking about cost reduction or when I'm talking about latency, you can imagine that what we are going to see in our simulation is a simplified version of what we are going to actually see in a real-world project with this number of tools. So just to give you also a quick overview of all the tools, these are the 5 categories of the tools that I've prepared for this test. The first one is inventory management, customer operations, order processing, analytics, reporting, marketing content. So these are the 70 tools that we want to pass to our large language model. Let me also quickly show you the schema of each strategy so you fully understand what happens inside the notebook. The first strategy is called naive, and this is our baseline. So in this strategy, regardless of the query, we will always pass all the 70 tools that we have to our LLM agent. The second strategy is called category-based. So here we get the query, then we use a keyword router to find the most relevant category for our query. And then we will retrieve all the tools that exist within that category, and we will pass them to our large language model. So by category, I mean these 5 categories that I showed you here. The third strategy is called retrieval-based. So we get the query, then we pass it to an embedding model, and we get the embedding version of our query. We also have a vector database that contains the embedding of all our tools. We perform a vector search using our embedding of our query, and then we retrieve the top K most relevant tools from that vector search, and we pass them to our large language model. So here, K is 10, but you can change that based on your use case. And finally, we have the hybrid method. So we get the query, then we use a keyword router to find the most relevant category to our query. Then we also perform a vector search among the tools that exist within that category, and we find the most relevant tools, and we pass them to our large language model. So this is the hybrid strategy. All right, so let's now go through the code together. Here, I have already prepared the vector database that contains the embedding of all our tools. You also have access to all the schemas that I just showed you, and of course, in the project, you have access to all the code that I implemented for this test. Perfect. So the first step is to load the libraries. So we need libraries like pandas and matplotlib for processing the database and also visualizing the result. But we also need OpenAI because I'm going to use GPT-4o Mini as my LLM agent. So the first step is to initialize the tool database. I mentioned that we have 70 tools, and we have 15 tools for inventory management, also for customer operations, and for order processing. And we have 13 tools for analytics reporting, and 12 tools for marketing content. Next, we have to define the test cases. So I have 11 tests here, and 3 things that I had in mind was, first of all, they should be realistic. They need to contain the expected tools that should be called with each one of them. And also, we have to include the category in those tests. So for example, you can see it here: process a full refund for order with this number and send an apology notification to customer with this number explaining the refund has been issued. So the expected tools here are process refund and send customer notification. The category is customer operations, and the description is refund with notification. So this is test number 1. You can go through the other tests as well. My goal here was also to pose different challenges with each one of these tests here. In the next cell, I have some helper functions that allow me to run my test. The first function is count tokens in tools. So there are other ways that you can count tokens in a more accurate way, but for this test, I just went with a very simple strategy. So with a rough estimate, each token is equal to 4 characters, and that is how I'm counting it. Calculate cost. For that, we have the input price per million tokens and the output price per million tokens for GPT-4o Mini, and that is how we can calculate it. We have extracted tool calls, we have check accuracy, and we have run test with tools. So this is where we define the LLM prompt. I chose a very simple prompt here. You are a helpful e-commerce assistant. Use the provided tools to complete user's request, but you can also update the prompt and give it more context. And now we can start and run our test. The first test is on our baseline, and this is essentially what we want to avoid in a real project. So the expected issues that may occur here is, first of all, we are going to see a high token usage compared to all the other methods. The second thing is the slower response time, of course. And then we may also see some tool selection errors. And finally, higher costs. So one thing to note here is that GPT-4o Mini by itself is a very powerful large language model. The tool selection error occurs especially if you are using open source models or smaller models than GPT-4o Mini. But even with GPT-4o Mini, we can see that the model sometimes can get confused. So let's see the test result here. Let me open it. So if we look at the test result, we can see that the model almost had a perfect performance. So for example, if we check the first query, process a full refund for this order number, and send, so this is the query that we saw earlier, the expected tools were process refund and send customer notification, and model successfully retrieved both. This is the case for almost all the queries. But if I scroll down, for query 9 and 11, we can see that the model got a little bit confused. So in this one, instead of 2 tools, one get customer details and the second get customer order history, the model only retrieved the first one. And the interesting case is this one. So the query is generate a comprehensive revenue dashboard for Q4 and also forecast inventory demand. Expected tools were generate revenue dashboard and forecast inventory demand. This is very clear from the query, but the model retrieved generate revenue dashboard successfully, and for the second one, it retrieved get top selling products, which is totally irrelevant. So this is a perfect example of how even GPT-4o Mini can get confused. So also, just as a reminder, in our tools, we don't have any code implemented inside any function. And if you know how we convert those functions into a JSON schema before passing it to the large language model, you can easily understand that if we actually implement a process inside these functions, that is just going to make it much harder for the model to go through those functions because it is receiving a much bigger context in its input. Now let's go through the key observations for our first approach. GPT-4o Mini had a perfect performance on clear, well-structured queries. It successfully handled parallel actions when clearly stated. And it didn't need any routing because it could access all the tools directly. So this is definitely not the case for smaller LLMs because they have a smaller context window. So keep that in mind that if you use open source model or smaller LLMs, this is going to be a bottleneck there. Then we have key insights. With all 70 tools, GPT-4o Mini achieved 92.4% F1 score. It had a very high token usage. On average, 3,663 tokens were used, which is 10x more than optimized approaches, which we are going to see in the rest of the notebook. Ambiguous queries still caused 50% recall drops. Distractor keywords could mislead even with full tool access. and the cost was 0.0064 in total. All right, now let's go through our first solution, which is category-based routing. Our expectations here are lower token usage, better tool selection, faster response, and lower cost. Let's see if this strategy is actually able to satisfy these requirements. In order to implement category routing, we need different words that would trigger a specific category for us. For example, if the query contains stock, inventory, reorder, warehouse, or supplier, this method automatically chooses inventory management category in my tools. So as you can imagine, these lists of words are going to have a direct impact on your accuracy. So you have to choose them very carefully. You can choose them based on your historical data, your business needs, etc. But these are super important. And if we just run these words on our test data, you can immediately see that we have 3 queries for which our system could not choose the right category. This is the first one, this is the second one, and this is the third one. And this is before even we pass the tools to our GPT model. So I think the bottleneck and the problem in this strategy is kind of clear right now, but I will mention it in a moment. And if we just go through the result, and again, I haven't passed it to our GPT model, this is where I'm doing it. But if we just have a quick look, our category-based strategy had the accuracy of 72.7%. So from now on, since we want to pass those tools to our GPT model, the only thing that can happen is that our GPT model might also make a mistake and make the accuracy even worse. Okay, so these are the 3 tests that we failed on that with this strategy, but I will talk about them later. So in this cell, as I mentioned, we want to pass the selected tools from the category to our GPT model. And if I show you the result, you can see that the model is doing a good job on the first one, is doing a good job on the second one, etc. But let me go all the way down and show you what actually happened. So if we go through all the 11 queries, we can see that the average tool used was 14, which is significantly lower than the naive strategy. Average precision was 77%, average recall 72%, average F1 score 74, perfect match 7 out of 11, average latency 1.72, average tokens 848, and total cost was 0.0017. So you can quickly see the trade-offs here. We saved cost and also had a faster performance, but our accuracy was clearly much lower than the naive approach. Let's see it in detail. The F1 score was 74.2%. I'm not going to go through the failure analysis here. Feel free to pause the video and check it for yourself. But the trade-offs here were 76% token reduction, 73% cost reduction, 15% faster performance. And when routing works, we have excellent tool selection. Rather is a single point of failure. We could not handle cross-category queries. Keyword-based routing is brittle, and lower accuracy was also something that we saw here. So category-based routing trades accuracy for efficiency. It is 76% cheaper, but 20% less accurate. The router quality determines overall performance. A bad route means complete failure. So now let's go through our second solution and see if we can fix these problems. So here, we expect to have a better tool selection accuracy. We also expect to have a lower token usage. This should work across categories, and this should be our most flexible approach. So let's see how it works. This is the cell in which I execute the workflow. So as I showed you on the schema, we perform a vector search. We choose the top, actually I can show you right here. We choose the top 10 relevant tools and we pass those tools to our GPT model. Let's see the result together. So if we just quickly go through the questions, the first question, we can immediately see that our model could not perfectly find the proper tools. It only found one of the 2 tools that were expected to be retrieved for this query. The second one, we had a perfect match. Third one, perfect match. Let's go down. I can see that actually the model did a great job, but let's see the summary here. So tools retrieved 10, average precision 100%, average recall 90.91%, average F1 score 93.94%, perfect match 9 out of 11, average latency 1.76, second average tokens 646, and total cost was 0.0014. I think the numbers speak for themselves. This has been the best strategy so far by far compared to our previous two strategies. So let's go through the key observations here. Of course, we had the best average F1 score compared to our previous two methods. It was 93.94%, which was better than naive, much better than category router, and we had the same perfect match rate as naive, 9 out of 11. The semantic search consistently found the right tools regardless of misleading keywords, cross-category needs, and similar tool names. And you can also see the queries in which I tested those aspects. So I will skip the failure analysis. Again, feel free to pause the video. So why it wins? Because we don't have a routing bottleneck. Cross-category capability, it can find relevant tools regardless of category boundaries. It has semantic understanding. It matches based on meaning, not just keywords, and it had the optimal tool count so far. So 10 tools gives model enough choice without overwhelming the context window. The trade-offs here were, in terms of strengths, we had the best accuracy, 82% token reduction versus our naive approach, 78% cost reduction versus our naive approach, 27% better accuracy than category router, and it could handle cross-category queries naturally. Weaknesses, retrieval quality depends on the embedding quality, still fails on fundamentally ambiguous queries, occasional retrieval misses, and it requires ChromaDB setup and maintenance. Key insight, semantic retrieval with 10 focus tools outperforms naive approach with 70 tools. So more tools does not mean better performance. The right tools matter more than all tools. Okay, in the last strategy, we want to combine our category router with retrieval method. So we combine these two, and our expectations here are we get the best of both worlds because we expect our category router to provide the context and our retrieval strategy to find the most relevant within the tools inside that category. But I kind of think you already know what is going to happen. So if you run the test through this cell, we are going to get this result. Let me open it up. So the first query, the performance is good. The model was successful on retrieving the tools. The second query, the same. Let me scroll down and let's go through the summary. Okay, so average tool used is 8 here. So this is the lowest number of tools that we have passed to our GPT model. Average precision, 77.27%. Again, we are at the mercy of the quality of our category router. Average recall, 77.27%. Average F1 score, same number. Perfect match, 8 out of 11. Average latency, 1.68. Average tokens, 564, which is, again, the lowest number among all the strategies. Total cost, 0.0013. Here, I didn't include the price of our embedding model, though. So you have to keep in mind that when we perform a vector search in the retrieval strategy, we also pay for the embedding model. But that is much, much less than the GPT cost. Let's go through the key observations. Overall performance, 77.27% F1 score. The hybrid paradox was that we combined category routing with retrieval and we expected to get the best of both worlds, but actually it inherited the worst, the router's failure rate. Performance analysis, it was better than category alone, but it was much worse than pure retrieval. And these are the 3 queries for which this method failed to get the proper tools. And there was also a bright spot for this one, though. It successfully retrieved the right tools for test number 9, which was one of the most problematic queries for our previous strategies. So trade-offs here are we had the lowest token usage, we had the cheapest approach, it was the fastest strategy, it helps with ambiguity when routing succeeds, it has a good balance when routing works. So everything depends on routing. Disadvantages, router dependencies, so it inherits 27% routing failure rate, can recover from routing errors, 16% worse than pure retrieval, and the system is quite complex. So the key insight here is that hybrid approach shows that combining techniques doesn't always improve result. The router becomes, again, a single point of failure that limits the entire system. When the router works at 72.7%, hybrid is excellent. When it fails, retrieval can compensate because it is searching the wrong tool space. And in case you want to go with the hybrid strategy, just like the category router, you have to make sure that you have a very precise router because that is the bottleneck for these two systems. So let me also show you this image which summarizes everything that we saw together. It just gives you a better sense of what just happened. So on the top left, we have average tools provided to the LLM. You can see the difference, the huge difference between the naive approach versus category retrieval and hybrid. And I specifically want to emphasize on the retrieval method because that was the best strategy that we saw in the notebook. So here we have the F1 score. As you can see, retrieval was very close to naive. In terms of the average of F1 score, it was a little bit better, but in terms of the perfect match, both of them had 9 out of 11 perfect match in our test data. The average token usage, again, you can see the huge difference between our naive strategy and the retrieval strategy. Total cost for naive we had 0.0064 and for retrieval we had 0.0014. So in a production grade system that you receive probably thousands or hundreds of thousands of queries per day, you can see how significant is the impact of a method like retrieval for your LLM agents. And finally, the average response time. For naive, we had 2.02 seconds, and for retrieval, we had 1.76 seconds, which was, again, the better strategy of the two. So at this point, you know which approach I'd recommend when building agents with access to many tools. But I'm also curious to know what's your preferred method in this situation. Let me know in the comment section. If you found the video helpful, don't forget to subscribe. Thank you very much for watching, and I'll see you in the next one.